Hello everyone, this is the last minute revision tips for Unit 1 exam tomorrow. So first we'll be looking at some of the common concepts because to be honest this is what's going to determine your grade. First we have laws of motion. So when you look at this diagram you see a man paddling a rowboat. So there are two laws of motion at play here. What are they? Newton's third law and Newton's second law. The paddle exerts a force on the water backward. According to Newton's third law, the water exerts an equal and opposite force on the paddle boat forward. There is a resultant force on the boat forward. This point you have to mention. And according to Newton's second law, the boat accelerates. So I have covered two laws here. There is a third one, which is actually the first law. So Newton's first law is not that common in recent papers. So there is a very high probability of this appearing in your exam. So I have three scenarios here: card, cup, coin, a stack of blocks, and tablecloth being pulled under a plate. All of these have the same concept. I'll start with the card, cup, coin one. The force acts on the card. The friction between the card and the coin is negligible. So there is no force on the coin. So the coin remains horizontally at rest according to Newton's first law. Then you have graphs of motion. It's very important that you are able to relate one graph with another for the same motion. So all of these three graphs are for the same motion of a bouncing ball. You start off from a height, that's why you have maximum displacement, and since the ball has motion in two directions, so the velocity has values in both positive and negative axis. So you can clearly see from here the downward direction has been considered negative and upward direction has been considered positive. And all the downward sloping lines have the same gradient because the gradient of these graphs give you the acceleration of free fall, that is 9.81. And you see some spikes in the acceleration time graph. These spikes correspond to the times when the ball is in contact with the ground. The ground exerts an upward force on the ball. There is a resultant force on the ball upward. That's why the acceleration is positive upward. And while it's falling freely, whether it's going up or down, it has the constant acceleration of minus 9.81. Then you have projectile motion. So there are three scenarios of projectile motion. You have to have a very clear understanding of three concepts. So in scenario one, the projectile lands from the same height from which it was launched. So the total vertical displacement is 0, and since there are two motions involved, the acceleration throughout the motion would be minus 9.81. Scenario 2, the projectile is launched horizontally from a height. So since it was launched horizontally, the initial vertical velocity would be 0. And since there is only one motion downward, acceleration is just 9.81. Scenario 3 is the most interesting one. It's where a projectile is launched at an angle from a height. Since the projectile lands below the launch position, the total displacement is negative because it lands below its launch position. And since there are two motions involved, throughout the motion you take acceleration to be minus 9.81. My mistake, it would be minus 9.81, but I have written here 9.81. So please be very sure about this. So the next concept would be independence of horizontal and vertical motion. So these two are the two common scenarios where two coins launched from the same height, one given a horizontal push, the other one falls vertically, they both land at the same time. The most important bit here is they both land at the same time. Why? Because same height, same vertical acceleration, so it's going to take the same time according to S equals to half gt square, even though one has a horizontal motion. So this shows that the horizontal force that you gave to coin 2 did not affect its vertical motion. And the second scenario is whilst moving with a constant velocity, you launch something vertically upward. Even when you launch it vertically upward, it will have a horizontal motion which it was carrying while it was moving along with the person. And the best bit here is the ball will stay vertically above the skater at all times, because they'll have the same horizontal velocity, even though the ball was given a vertical force. So scenario 2 represents that the vertical force has no effect on its horizontal motion. So these two scenarios combined tell you that horizontal and vertical motions are independent of one another. Next up, you have momentum. So of course questions will be involving law of conservation of momentum, and you have this in both explosions and in collisions. Let's first look at explosions. In explosions, you start off with total momentum, which is zero, because the bullet and the gun was both stationary initially. So the bullet moves forward, and to conserve momentum, the gun recoils backward. And in conservation of momentum with collisions, total momentum before collision is equal to total momentum after collision. Always remember that in both collisions and explosions, momentum is conserved. Then you have moment. In all moment questions, the most important bit is to identify the pivot. Here you can clearly see the bar which is positioned at the ground. This point is where your pivot lies, because the whole thing moves about this point. So this point is considered to be my pivot. So the mass of the barbell, the weight attached to it, provides the anti-clockwise moment, and the person pulling it upward provides the clockwise moment. At any given point, if the system is in equilibrium, total clockwise moment equals to total anti-clockwise moment. And always remember, in all moment questions, always consider the force and the perpendicular distance from the force to the pivot. Next question is with work energy power. So it's one of the most basic concepts, but I have tried to pick up the two most complicated ones. So the first one is with a jetpack, and the second one is with a waterfall sort of thing. Both has a pump. Both of them have a pump. So the pump is doing two jobs. One is to raise the water through a height, and then giving it a velocity. So the minimum power required for both scenarios is work done per unit time, and work done corresponds to energy transferred. Now to the water, there are two types of energies that is being transferred to the water. One is gravitational potential energy, and the other one is kinetic energy. Both are provided by the pump. Fluid mechanics is pretty straightforward. So the most common questions would be the conditions for Stokes' law, using appropriate density for calculating upthrust, and determining whether Stokes' law is applicable. So for the third part, whether Stokes' law is applicable, you have to compare Stokes' law force using 6 pi eta RV with drag force. If Stokes' law force is equal to drag force, then and only then you can say Stokes' law is applied. Then you have solid materials. Comparing different materials using stress strain graph. Back in your mind, you have to remember that the area of the stress strain graph is the energy stored per unit volume, which is the energy density. The gradient of the straight section of the graph gives you the Young modulus. Also review why wires used in Young modulus experiment are long and thin. This is a very common question if you want reference. One of the most common ones would be from May 2019. Then recall why a material is most likely to break when it's undergoing necking. Where a material is most likely to break? The place where the cross-sectional area is the smallest, there you'll have the highest stress, and highest stress corresponds to highest strain. So that's where the material is most likely to break. And also remember how a force extension graph can be used to calculate Young modulus. So the very first thing you have to do from the force extension graph is calculate the gradient, and then tweak the equation of Young modulus and fit in the gradient, force by extension, and multiply it with area, cross-sectional area and length to calculate the Young modulus. So in solid materials, there are some combined concepts as well. So here you can see fighter jet being stopped on an aircraft carrier using arresting cables. So what happens is when it lands, the cable attaches to the flying jet and it's brought to rest. So whilst the airplane was moving, it had kinetic energy, and since it has to be brought to rest, all of its kinetic energy is transferred to elastic strain energy. So if you have to do some calculations, bear in mind that half mv square equals to half fx or half kx square, depending on the question. And now I have some general guidelines. Always, always, always start with section B. Solve show that questions first and answer them with one significant figure higher than the question value. Use your calculated value in the next part of the question. So if a question asks you to show a value, use your value, not the one given in the question, in the next part of the question. Memorize all of the definitions, for example, center of gravity, what is meant by equilibrium, what is meant by yield point, etc. Do not leave anything blank. In calculation questions of 3 marks or higher, always get started with the information given in the question. Do not try to calculate what the question is asking for in the first step, because that would be in the last step. Underline the keywords before starting to answer a question, especially all numerical values. Always draw a diagram, and if you cannot, visualize a scenario. If a diagram is given, add to the diagram. This helps you visualize the scenario more clearly. Expect questions from Unit 3, for example, when a certain instrument is more appropriate. In any measurements, we always try to minimize percentage uncertainty. Good luck with your exam tomorrow. Thanks for watching.